about 26 participants. I mean, not 26, 24. So yeah, I think we'll start. So good morning, everyone, and a very good morning. And it's a very interesting day today. So IBM and we Bangalore section affinity group have put together this tutorial. Thanks to the IBM team. These are practitioners who are going to be taking you through practical examples of the use of AI and ML. And we are going to be covering the fundamentals of AI, um, machine learning, and so on. So make the most of it and all the very best. This is going to be a hands-on session, so you should also be trying that. The other thing that we wanted to do is the certificates will be available after you, complete this course. Work on the examples and the tools for a week, and we will be sending out a quiz at the end of the week. And once you complete that and the feedback, you will also be getting certificates. So all the very best, and do make the most of it. And I really thank the IBM team, especially Pratiti, Janani and Parvati also, who have coordinated and brought to you a great set of facilitators who are also practitioners. So, yeah, I'll hand over the mic to Pratiti and Suranjana.
Hi. Good morning, everyone. This is Suranjana. Welcome to this tutorial, which we planned for all of you. So we'll start with the very basics of AI and statistics, and then we'll gradually move towards the more deep into the deeper applications of AI in the subsequent sessions. So let me share my screen. And we can go through all the concepts together. Yeah. So in this session, I'll be mostly talking about AI statistics and the very basics of machine learning. Or pattern recognition or AI, whatever you say, all these things are very basics to all these fields. And it is actually the backbone for many of the theories that we generally use in our day-to-day machine learning tasks without even realizing that they have been so important actually. So feel free to pause me anytime and ask questions or clarify any doubts that you have in your mind. And let's try to make it as interactive as possible. So basically, I'll be going through these topics. We'll start with a little bit of curve fitting. Then we'll go to the very important concept, bias and variance. We'll mostly talk about the Bayesian theorem, Bayes theorem, and how we can use it in the classification task. Then finally, we'll finish off with three important statistical concepts: confidence interval, central limit theorem, and hypothesis testing. So these are some of the references which I at least diligently use right from my student days. So the first two are very good books for pattern recognition and machine learning, very fundamental for statistical machine learning mostly. The third one is a statistics textbook, which is again, it has great content, great explanation. So most of the materials have been taken from these books. And any other references, if there is in the slide, is taken from those websites, which you can go and follow later on. Okay, so let's first ask this question: why do we need actually machine learning, right? So there are this data, of course, and we want to deduce the information from this data, right? So that is the whole purpose of machine learning, to understand the data and somehow to model the data. Sorry. So now what happens is that the problem is that even though we have the data during the learning time, it's not that we have all the data in the world, and that's why we need machine learning. Because if we would have all the data in the world, number one, the processing is anyway, like the storing and all those things is a challenge. But let's say we don't worry about those hardware limitations or any other thing, then it will be just a simple lookup problem, right? So generally, if the number of variations in the data that we have is very less, it actually becomes a lookup kind of table, right? But then the data varies. We love variations in our day-to-day life, and that gives rise to more and more varieties of data. Now, the idea is basically how do we learn these things in a very meaningful way, and instead of storing all the data that is given to us during the learning or the training phase, how do we basically model the data into more meaningful kind of representation and use those representation to reduce any kind of information during the testing time, or whenever some unknown data actually comes into picture. So that is the whole crux of machine learning, right? Now there are some issues. Means it's not that actually simple. There are some practical challenges. So the number one challenge is how do we model the data, right? So basically, when we do model the data, most of the time we have this assumption that the data is following some distributions. So now, what is distribution? Distribution is nothing but a way how the data has been arranged. Now there are these many distributions in statistics: normal distribution, Poisson, binomial. Any questions?
ನೋಡಿಲ್ಲ ಏನಿಲ್ಲ ಅವಾರ್ಡ್ಲಿಂದ 5 ನಿಮಿಷ ಆಯ್ತು ನನಗೆ.
So if there are no questions, so please kindly mute yourself, or else feel free to ask me any questions. Yeah. Okay. So let's say there are so many distributions, and then when we assume that we will represent the data in terms of a distribution, then we will actually assuming that the data has been drawn from a particular distribution, or the data has been arranged in a particular way. It's not totally random, but it follows certain kind of patterns, and we assume that, and we follow our algorithm using that assumption. Now, what happens is that during the training time, we do this assumption, and we may say that that the underlying distribution is so and so. But during the testing time, or when actually the real when actually the data comes, so it may not follow the exact same distribution, right? It may be a little bit here and there, and that basic assumption that the data should actually contain this much of distribution, and whatever things we have learned from the training data, it may not entirely hold good. It will hold good with some errors, right? So that is one of the main things that we want to try to minimize during the whole training process of the machine learning. And then not only that, in many cases, especially in supervised classification, right, we actually need labels of the data. So labels are what basically means, as we all know, in supervised classification, the task is basically to understand or to categorize the data into one or more class. So we do need some class labels for learning the model, right? Learning any kind of statistical model or any kind of machine learning model. Now, it so may happen that all these labels are not always very, very gold standard or very pure. There may be some noise while doing the labeling. So there are labelers or there are human annotators who will do the labeling, right? But sometimes the data or the task itself is so difficult that the labeling process itself becomes very clear. It becomes very confusing. So someone, I think Shilpa is mentioning that she is unable to hear. Am I audible? Am I audible to everyone, or can most of you hear me?
Yes.
Yes.
Yeah.
Okay. Okay, Shilpa, it may be a bandwidth issue from your side, or it may be, yeah, try to increase the volume or try to disconnect and reconnect again. I hope it solves the problem. Okay. Okay, so let's move on. And then again, like, so another assumption is that, when we actually try to model the data, or we try to learn any kind of model, again, we do assume a lot of things, assumptions like this model is actually perfect for the data, or even in the model, there are a lot of components like the loss function, the optimizer, etc., which will be walked through later on. So all these assumptions may not be actually holding good for the particular data in our hand, right? So main problem is basically in any kind of machine learning algorithm is number one, to understand the data, and number two, choose a correct kind of model or correct kind of assumptions to do the task at hand. So if it's a classification task, we'll be training a classifier, but the correct set of classifiers must be chosen. That is the whole idea. If you can understand the data, if you can understand the task, most of your problem are solved. The next thing is just to tune the parameters, right? Which is basically mostly a kind of engineering kind of work. But understanding the data and understanding what kind of model will be beneficial for you or will solve your problem is the whole dicey thing in the machine learning area. So let's start with curve fitting. Okay, so this is, as we know, like curve fitting is nothing but we have some points, and the task is basically to represent the point using a line. The line may be a straight line, it may be a curved line of any degree, that is okay. But basically to represent the whole data using a particular line. Now what happens is that this is basically, as you see here, this is the very basic function for curve fitting. What happens is basically, there is this curve that we want to try to fit, and then we will represent these points, which are basically these original points, as per the projection of these points on this line, which will be given by this particular function y of x. W is basically the parameters of the line. So, and then these are the true values, this Tn are the true values. And what we want is that this line, the projections of these points on this line should be as close to these true values that are given to us. So this is the whole, you know, crux of regression or curve fitting. And we want to minimize this particular difference of the projection of the points and the actual points using this curve. And what happens is that, like now you just have this curve fitting and you have to assume that, you will fit a curve. But what kind of curve will you choose? Is it just a simple straight line, a parallel line, straight line parallel to the axis, or it is a, little bit of more complicated straight line? Basically, this is just has one extra parameter or one extra degree of freedom. So do you want to go with this line or a more, curvy line or an extremely curvy line, right? So you have to decide before fitting, before doing finding this loss function, what kind of a function this YB. So now how will you actually choose? Now, if you just see, like, this is what, this is basically the projection of the given points on the line and the true points, like the difference between the two, and we are taking the square of this line, sorry, square of this difference, just to make this thing more mathematically, intuitive. This will make this whole equation differentiable. So one of the main thing is that for any kind of, most of the machine learning problems, generally we deal with a loss function, right? So the loss function is where we want to put all the characteristics that we want to have in our model, and we generally try to have a good parameter estimation using that particular loss function. Now, this loss function, to do that whole parameter optimization, there are some properties of the loss function. The number one, and it should be definitely be met, is the loss function should be differentiable. So what happens is that if it would have been something, a non-differentiable kind of function, then that would have been a problem for us, right? Because the whole process of optimization goes through different kind of differentiations, and we try to achieve our result using that particular differentiation strategy only. So the square of this particular function makes it a nice function, a differentiable kind of function, and we are happy with this kind of loss function. Then there are other properties also, like if the loss function is continuous, it is well and good. There are some non-continuous loss functions also. They are hard to optimize. People do avoid them, but yeah, for practical purposes, for certain tasks, they are there with some approximations. Anyway, we are not going to go through that because of the time limitation. But anyway, so what happens is that, let's say we look at this particular curve, right, where the degree of this particular function is 9, or it's a 9-degree polynomial that we are fitting on this curve. Now, if we actually put this particular function in use, we will see that this will actually become 0, because every time the curve actually passes through the points which are given to us. So the projection is actually the point itself, and then thus for every point this becomes 0, right? And we essentially get this particular EW, the value of EW, as 0. But do we really want that? Means, do you think this kind of a curve fitting is actually good? Actually, no, right? Why? Because it lacks generalizability. So this is very good for this set of points. So how many points do we have? I think 15 or something like that. So this is very good for this many kind of points. But then our world is not limited to these points only, right? This is just a training, and during testing many more points will come into picture. And if we actually use this kind of function, then it will be a difficulty for us during the testing time. Testing, it will fail miserably. There is no generalizability that has been captured in this curve. However, like if we look at this particular thing, or again here, we'll see that the model is very simple. However, it does not do this justice to this particular equation. Justice means these values will be really, really high, and then we will not get something, a minimum kind of EW, or the loss will be really more. So that is again a problem for us. So mostly this and this are also very simple models to work with, but somehow this third order polynomial, it fits very nicely. It does not pass through all the points, but it at least captures the pattern of the points that are given to us in a very nice way. So it actually has a balance between the generalizability and also the correctness, or basically to reduce the loss function in a very nice way, right? So again, this is, as you can see, like every time, whenever, like in any phase of machine learning, the idea is to find that particular balance in finding the right model, balance in finding the right parameters for a model, and everything. So this is what we are trying to do, and this actually gives rise to a very nice concept called regularizer. So regularizer, what it does is basically it adds a term here. So what happens is that if we just try to minimize this particular thing, as I was saying, like for this 9-order polynomial, this loss function will become 0, and if you use only this particular equation, then perhaps we should not complain as per the loss function, right? It does the job perfectly as per this equation. But as we said, like we want generalizability, and we do not want this W, or the parameters of the curve, to shoot up here and there. It should have a balance, and that means the values, the real values. So this is actually a vector, because we are talking about a 9-degree polynomial. So it will actually have 10 parameters along with the intercept, right? So any line or any curve, it will also have this intercept also. So it will actually have that many number of parameters. So what happens is that these parameters need to be estimated. So our task is basically to estimate this thing, but we also don't want the values of these parameters to go here and there. It should not shoot up to a very large value. It should maintain that particular balance. So we introduce something like this, where this alpha is again a particular kind of variable that we introduce, and this is called a regularizer. And basically this is a function of W. Here the function of W is the norm of the particular vector that we are using. And what it does is basically try to keep each of these values of W to in a particular range, so that during the testing time the model remains tractable. So this is very, very important. Now there are actually different kinds of this regularizer which serves different purpose. So one of the most commonly used one is basically the norm of the vector. There are some cases where actually we try to actually estimate matrix. So instead of this W being a W being a vector, it can be actually a matrix. So in that case, we can actually have trace of a matrix, determinant of a matrix. But anyway, that is not what we are discussing right now. So here for a vector, the norm of a vector is a very good function for to be used in kind of regularizer. Now there are the next, I think the next important regularizer function is basically the absolute value of the vector, or basically the one norm. So it also serves another different purpose, which is highly usable in any kind of sparse matrix optimization or sparse vector optimization, right? So there are actually geometrical interpretations of this regularizer which one can look into. But basically what it tries to say is that there is a unit closed ball kind of, if you just visualize the coordinate geometry. So there is this circle, and all the values of this W should fall within that particular circle. That is the whole interpretation. So somehow we are trying to limit the values of the W in a particular range. Now now, of course, like for all practical purposes, we do use regularizers in all the models. It is inbuilt in most of the algorithms or most of the packages, tools that we use. So we are well and good. Now, basically, this comes this very important concept of bias and variance. So we were saying that, this ninth degree polynomial, though it does a very good job in minimizing this particular equation, it is not desirable. Now, actually, when we add this particular term, the regularizer, all this ninth degree, the W in this ninth degree model, these W's will actually have a very high value, and this will shoot up. Now, we don't want that, right? We want to minimize this particular thing. So even for this particular model, this 9-degree model, even though this particular term goes to 0, this will be very, very high. And thus, we change the loss function, and even for this 9th degree polynomial or 9-degree curve, we will see that, this is not giving us the minimum kind of value. However, this third order polynomial, this will actually have a much lower value of W, and this also will be reasonably low. It won't be 0, but it will be reasonably low. And together, they will perhaps give us the optimal or the minimum value of this loss function. So that's how important, that's why this regularizer is important. And that's why, to choose a correct model, we should always use a good regularizer. And regularizer, it's not only doing this particular purpose, it sometimes enhances certain characteristics that we want in our model. For example, the absolute value, if we take the absolute value of W, as I was saying, it will actually ensure that our W is sparse. That is, most of the entries in our W will be 0, and very few will have positive value. So sparse vectors are many times desired in many of the tasks. So we can also enforce certain characteristics through regularizer. So now let's talk about this very important concept of bias and variance, right? This is extremely, extremely important. Bias and variance is perhaps now very well known as some concepts like overfitting or underfitting of the model. I think that is more popular term now, but nevertheless it comes from bias variance, and it is extremely important, okay, not only while deploying your model or while understanding which model will be used, is to be used, but even for your interview questions, it is a very important concept, and people love to talk about this particular thing. So what is bias? So bias is nothing but how good your prediction is from the true value or the labels that have been given to you. So as per the definition which I found somewhere, it says like it's the average difference between the predictions of the model and the true values that are to be predicted. So basically high bias means that the difference is low. That means you are close to the model that is there. And mind it that these all things are mostly calculated for the training set only. Excuse me. So basically whenever we do any kind of analysis, there is this training set and a validation set. So we try to see the errors in both training set and the validation. We try to basically fit the model on our training set and try to see how the error is changing or how the loss function is changing in our test set, right? So now basically when the difference between the prediction of the model and the true value is minimum, especially in the train set, then what happens is that it is actually a kind of oversimplified model. So basically the idea is that in your training set, the loss is low, but in your validation set, the loss is higher or significantly higher. It will be higher definitely, but it is significantly higher. So in that case, actually it's a over simplified model that you are considering, and perhaps it is underfitting. Underfitting means it is very nicely representing your training data, but it is not generalizable enough, and it is it is just not understanding the pattern when validation set is given during the test time. And then variance. So what is variance? Variance is basically to ability of a model to learn a more generalized solution. So what we want is not a very complex model. Again, the complexity actually varies based on the data that is there in your hand. Let's say there is a data which is quite quite solvable using a second degree polynomial equation, but then you are using something like a fifth degree polynomial equation, then that is a complex model for you, right? Means it could have been solved using using a fairly simple model which has a less number of parameters, but somehow we are going for a higher, much more complex model. So high variance generally means that it is a complex model and it is overfitting your data, right? And this is again a very popular diagram you will see in the internet or any other books. So the idea is that this bullseye here, this is the actual truth, and as you are moving away from this particular actual truth or the true level, you are basically encouraging more error into your predictions. Now high bias, low variance, so these are how the predictions will be scattered all across this particular figure. What we want is basically this low bias and low variance, which fits very nicely to our predictions, not only for our training test, but also for testing or validation set. And high bias, basically this underfitting, that means the labels are far from the true labels. And low bias is also is not good. It is actually all the points are scattered all over the place. That means it is not understanding the pattern of the data or not being able to deduce basically what it should do. Basically it's underfitting. It is just randomly selecting certain things without actually understanding the data. So this is what it tries to do. And of course, anyway, high bias and high variance is anyway bad. It should not happen at any case. So it becomes also very intractable to correct your model. So it may happen that, whenever you are actually trying to tune a model, you will be always looking at the loss, how the loss is changing in your training data and your validation set, right? So let's say both are decreasing in a very nice way, then well and good, you are in this particular range, it's very good. Now let's say your training error is decreasing, but your validation error or the test error that you are looking into, it is actually increasing in the opposite direction. Then actually this is, in this case, you have a high bias. Perhaps, you should actually consider a little bit more complex or more sophisticated kind of machine learning model, and then this should possibly solve this particular thing. And let's say other things, or it can be actually this particular case also, where you have a very low bias, high variance, and it is overfitting. Now another thing, the actual error that we see, or the particular value of the error, this can be actually represented as a summation of the error that is happening due to bias, error that is happening due to variance, and the error that you cannot reduce. And this particular error actually comes from different things, like there is this noise in the data, noise in the label, some assumptions which anyway you have to take for the processing, like like the distribution. Anyway you have to have that particular assumption, this model is following certain kind of distribution. It may not be exactly correct, but some assumptions have to be made, which makes this as irreducible error. But then these particular errors, which actually occurs due to bias and variance, this can be reduced, and this is what we want to do. We want to reduce the bias and variance of the model that we are learning, so that our overall error becomes small. So this again, like as I was saying, like the bias variance should be reduced, but then this is a kind of trade-off that we have to do. Most of the times what happens is that as the bias increases, the variance decreases, and vice versa. So how do we do that, right? So this is again another example which shows very nicely like what is overfitting, underfitting, and what is a good balance, or what is the desired thing that we want to have. So overfitting, as we can see that there is this high variance and the curve is passing through almost all the points very nicely, but there is hardly any generalizability. And high bias, like the model totally fails to understand the nature of the pattern of the data. It is an oversimplified kind of model. It also does not work very good. And this good balance is what we want to have, where the bias and the variance does have a very good kind of balance with each other. So this is again a very like any bias variance material you go and read, you will always have this figure. So this is the algo complexity. As the complexity increases, your variance decreases, your bias increases, and what kind of algorithm should you use, or what kind of a model should you use? Basically something in this range, right? Where this is basically the total error. This is the error that you will get, and what we try to do is basically go for the model which gives us the minimum validation error, right? So, and if we actually go and observe the bias error and the variance error, bias is actually always taken as square of the bias error, then we will see that this point also gives us a very good trade-off between the bias variance problem that we just talked about. So another thing, when we are actually saying the complexity of the model, or the model a little bit more complex model or little bit less complex model, what does it actually mean? So we'll all agree that this particular line is kind of a very simple model, and this particular curve here, which is I don't know how many degree of polynomials, this is a very complex thing, right? But then what makes it complex, or what makes it simple? Any idea? It's actually the number of parameters that you want to estimate. So here, if you see, this is just a line parallel to the x-axis. So there will be just one parameter to estimate, that is the intercept. It's just a one parameter. The model has one parameter. Whereas if you want to, model this particular red curve here, it has so many. It is a highly complex one, because the degree of this particular curve is must be quite high. I'm guessing it's more than 9. Or so basically what happens is that there are so many parameters here that needs to be estimated, and more the number of parameters, it becomes difficult for us, because for every estimated parameter, there is a particular margin of error that we consider it's okay to have. Now, whenever there is this margin of parameter, whenever this number of parameters increases, so the margin of error for each of those parameter estimation also increases. And thus it becomes more and more difficult to train a complex model rather than a simple model. Here the margin of error will be very, very less compared to this. So complexity of a model mostly depends on the number of parameters to be estimated. So thankfully, we are in a world where we train very, very deep neural networks, which are billions of parameters using very sophisticated techniques. But nevertheless, they are hard to train. There are, they are very complex models. And what I'll suggest is basically, if your data can be modeled using a simpler model, always go for it. It's not only very easy to interpret, but it is also very easy to handle the training and other things. It becomes much more tractable. Just whenever you are having a model, if you just think that, oh, I'll use the most complex or the state of the art model to solve my problem, it always does not make sense. The model should be chosen according to the data that you have in your hand. It should be interpretable enough. The training should be fast. Training should be nicely done. And most importantly, basically, it should be generalizable enough, or it should be complex enough to understand the parameter of the pattern of the data. So this bias variance trade-off, like that is the whole idea of machine learning, as I said earlier, right? Understanding the data and understanding what model should actually fit well for your data. So this whole concept of what model will actually fit well in your data, this particular thing is backed by this particular very important concept of bias variance. And this bias variance is, as you can see, like this is more the cool terms for this bias variance trade-off is overfitting, underfitting. So many a times we come across these situations where this model is underfitting or overfitting by observing the training and the validation loss. So whenever things are not working in the way you want, that means you are not using the correct model for your data. Okay, any questions so far? Please feel free to ask any questions, or if you need a clarification. Okay, then we'll move to the next part of this particular session, which is more on the Bayes theorem and how Bayes has been used for the classification task, right? So Bayes is basically, Bayes theorem is a very important concept in statistics, and I'll say it is the base of any kind of classification task that, not any kind of, like, it is perhaps one of the most first model that we actually have used for solving our classification task. And the probability and the concepts that we generally use to learn Bayes theorem, it has a long reaching effect. Generally, we use this in many other classifiers as well. So, and the whole concept of Bayes is actually comes from the probability, linear algebra a little bit. So I thought it was a good idea to introduce these terms if someone is not, someone needs to brush up this skill, these concepts. So this is a table that shows, so basically x and y are two variables here, and this is a table which shows like if x has a value of xi and y have a value of yj, then what can be these values. So this is a discrete probability that we are talking about, or discrete samples that we are talking about. So let's say there xi has some value. Let's say if when xi is equal to 3, yj can have only a certain number, as a certain value as its number. Okay, so that is this particular table or the distribution table that we are considering. Now this is basically all the values that the x can have for this particular column, and this is the rj is basically all the values yj can have for a particular row. And some of the very important terms that you will always hear is marginal probability, that is probability of x being a particular value. Joint probability, that means x is also having a particular value and y is also having a particular value, then what should be the probability. And a conditional probability, that is given x is having this particular value, what will be the value of y. So basically we want, most of the time we want to deduce this conditional probability, that is given x, what is the probability that y will have this particular value. And to support or to understand this particular or to estimate this particular probability, we will need the joint probability and the marginal probability as well. So this is actually very much used in our classification task, right? Given a particular instance or particular data point, what will be the label, or what do you think is the label? And that is how we actually model most of our ML classification models, right? So this is very, very important in that way. So these are some of the very basic probability axioms, sum rule and product rule. So I hope there are these other axioms, very preliminary axioms of any kind of random variable, that it should lie between 0 to 1, it should sum up, or the integration should be always 1. All those things are very elementary. Anyone can go and brush up those. There are tons of material for those things. But then this sum rule and product rule is something which is used quite a lot in Bayes theorem and in any other kinds of, the actual mathematics behind most of the classifiers. So just to brush up, I have given it here. So this is in terms of discrete samples. So this becomes a summation, basically probability of x. It actually becomes a summation over y for all the joint probabilities, and the product rule is basically a summation of the conditional and the marginal one, right? Yeah, so again, just to brush up the discrete case where the sample is discrete. So A is basically our seed or the sample. What happens is A can contain only this many number of values, or you can also, kind of draw the similarity with categorical variables, where the variables can have only this many number of instances. There cannot be any other value beyond that particular set. So that is the discrete case, but most of the cases we do have continuous values where our variable can have any value within a particular range. So in that case, we take the integration, and this fx, we term it as a probability distribution function, right? So, and again, like when this distribution function comes in mind, there are certain distributions which we prefer in machine learning. It's not that, others are bad or others are, does not happen. It's not like that. But most of the cases, due to practical, implementations, we have seen that something like Gaussian, binomial, these kind of distributions, or Poisson, right? These kind of distributions are very, very, very frequently occurring, or can be used quite a lot to model the data. and then that's why most of the machine learning algorithms, especially the statistical ones, right? So all the derivations are done keeping in mind that the data is following a particular distribution, and those distributions you will see are mostly following either Gaussian or binomial, polynomial, this kind of more popular distributions. So here I have given example of Gaussian distribution. So this is the first, so basically what is Gaussian distribution? It's basically a bell-like structure, and it has got two parameters, mean and standard deviation. So this makes it very nice that you only have to, calculate two different parameters. So in a univariate case, this becomes our equation with mean and variance, x being the sample, and with different kinds of mean and variance, your Gaussian will vary, right? In a multivariate case, so this becomes our equation where d is the dimension. So if it is a two-dimension, it becomes d will have d is equal to 2. If it is 100-dimensional kind of space, it will have some certain kind of other values. But then this is the particular equation, and now what we have to do is to estimate this mu and sigma. Now, what happens in a multi-dimensional case? Like, let's say, when d is equal to 100. So here, though it's like, it says like, it's mean and variance, just two variances, but this mean is actually a vector. This variance or the covariance matrix is actually a square matrix. So you are not only dealing with two, but you are dealing with, I think this will be a 100 cross 100 matrix, and this will be a 100-dimensional matrix. So 100 cross 100 plus 100. So 100 into 101. That many amount of variables you have to estimate. So the complexity increases as the dimension increases, and dimension is basically determined by the dimension of your data, right? So so basically what I'm trying to say is that this complexity of the model increases with the dimension of the data that you are handling. And so again, we will walk through three different cases how the Bayesian classifier can be treated, from a very simple kind of classifier, linear classifier, to a quadratic kind of classifier, using certain assumptions that are made mostly on the covariance matrices here. Okay, so let's talk about the Bayes theorem. It's a very simple thing. Most of you have seen this equation. It's very simple, but for the completion, of the lecture here, I thought it's a nice idea to include this particular thing. So the idea is that there is this x and y. These are random variables, and what we want, so basically x and y, the intersection of x and y can be represented into two different ways, and then when we equate these two things, yeah, we get the Bayes theorem here. So this is just, we are equating this because both are excuse me, yeah, both are actually expressing this intersection point here, intersection region here, and just bring one as a denominator, and you will get the Bayes theorem that we are all familiar with. Another thing is that now this is a marginal probability. So if you just replace this denominator by this particular thing, this is another form of Bayes theorem. Now, for all practicality, we actually consider only the numerator. This is considered as something which is on which we do not have much control. So we generally say that this is the posterior, but that is the y given x. This is the posterior, which is basically directly proportional to the likelihood and the prior. So this is our likelihood, this is our prior. So posterior is basically the so in most of the cases for classification tasks, you will see that y is the label and x is the instance. So we want to actually try to find like what is the probability that given that particular instance, the probability, what is the probability that this particular instance belongs to class 1 or class 2, like whichever is your class, right? That is what is our posterior. So it is a belief that the unknown label, on the unknown level, once you have seen the x or once you have seen the data. So this is our posterior. Likelihood is that, So given this particular instance that is there, what observation has been made on this particular, that this particular label has been, has been occurring with this kind of instances. Mostly this has been obtained using training data. And this is the belief on that unknown label, or this is the prior. So many a times for simplicity, we do not consider the numerator, we consider the likelihood and the prior. And again to make that more simpler, we can also ignore the prior and we can say that is a particular constant, and or that will never change, and we can straight away consider posterior is directly proportional to the likelihood. So these are different kinds of assumptions that we make to simplify all our calculations, and this leads to different kinds of popular algorithm or popular kind of estimation that you may have heard of. So this particular when you consider this particular assumption that posterior is proportional to likelihood cross prior, this gives rise to MAP estimation. You may have heard maximize a priori, or when you just say that prior is also fixed and posterior is directly proportional to likelihood only, that gives rise to ML kind of estimation or maximum likelihood estimation. So as you see here, right, so perhaps these are more popular terms, MAP or ML, but all these things actually come from very basic concepts, Bayes theorem and other things. So as I was saying, right, so based on that particular assumption on the Bayes classifier, there are different kinds or different complexities of classifier we can design. So let's talk about little bit about that. So what happens is that, like, this is a case of a binary classifier where we have two classes, y1 and y2. And what here we are interested in is to calculate the decision boundary. So Gx, let's say Gx is our decision boundary. So what happens in a decision boundary? The probability of class 1 and probability of class 2 both are equal, right? So this particular figure, if we just try to take the difference of, posterior of class 1 and class 2, this should give rise to 0 in the decision boundary. But in the decision region, if Gx is greater than 0, it's class 1. That means this one is higher, this posterior is higher. Then we assign our classes to G1, class 1, or else to class 2, right? And then we can actually, have a much more interpretable kind of equation in terms of this, especially when you have this assumption that your likelihood is following a Gaussian distribution. Then we can actually have this particular Gx in this particular kind of thing. So again, note that, for all practical purposes of solving or, estimating the parameters or solving the equations, we do take certain kind of, mathematical transformations. So in most of the Bayesian kind of estimations, or, Bayes theorem, Bayesian learning, you will see the log to be used quite a lot, because in Bayes, in Gaussian theorem, so most of the underlying distribution is Gaussian, and then it has a exponential kind of factor into it. So to bring down and then to make your life simpler using differentiation and other techniques, we always try to take the logarithmic version of that. So you must be aware of many important, this important loss function, log loss, right? So it mostly happens, because we take the log of that for to do away with the exponential part of the loss function, so that our life becomes easier in terms of calculation, in terms of mathematical calculation, in terms of handling the range of the parameters. Things becomes much more easier when we consider log in many cases. Yeah, so this is basically the equation we want to calculate using the mean, variance, and the sample. So this is for class I. So what happens is that for many cases we consider, for this particular binary classification cases, we consider calculating these equations and try to get an equation for Bayesian classifier. Now there are a lot of simplifications that we can do to make the Bayesian classifier very simple to a much complex kind of classifier. So the first thing is that we can actually consider this all the covariance matrix. So the covariance matrix for all the classes as a constant kind of thing, where sigma is the only variable here and I is the identity matrix. So it becomes the only parameter that we need to estimate. From a d cross d parameter, we actually calculate this one parameter only, which is the sigma, and then our equation becomes very, very simple, something like this. So these are constants. These are all constants. Once we actually estimate mu, once we actually estimate mu and sigma, we can do this from the data. We can do it with things like ML estimation on MAP. This is basically our equation. This is basically our classification equation. So if it is WT x minus x0, so this is our equation. If it is greater than 0, then we send it to class 1. It is less than 0, we send it to class 2, or it actually depends on the data, how the data is aligned. But then this becomes a very simple linear classifier. And the another thing is that it not only becomes linear, but it is basically orthogonal to the line joining the two means. So let's say this is our class 1 and class 2, and there is this line joining the two means. So this is our decision boundary. So it will be always orthogonal and it will pass through the midpoint of these two means. So that is basically what is happening here. So it's a very simple classifier with lot of assumptions by reducing the number of parameters. Now a little more difficult case where basically we consider the covariance matrix, but then we do not we consider that all the covariance matrices for all the classes are same. And then,
sorry to
yes,
interrupt you, but there is a question. Somebody is asking, what happens if the underlying distribution is non-Gaussian?
Non-Gaussian, yeah, it's a very good question. So basically, here, right? So if the distribution, so basically the Gaussian assumption comes from this particular equation here. But then before that, we have this particular equation, or we can take the log, or if we can skip the log also. But basically the idea is that this Gx is basically a summation of, can be represented in terms of the likelihood and the prior. Right now that we are taking log x, we do it a plus, but otherwise it is a multiplication kind of thing. Now the assumption that this is a Gaussian distribution actually holds during the calculation of this particular probability, either likelihood or the prior, right? So now if it is a different distribution, these values will change actually. So we have to calculate again from the beginning how these values are changing. So this is not a Gaussian distribution anymore. Let's say it's a binomial distribution. So the binomial distribution will have certain equations for this prior. So we have to put this and for this post likelihood and the prior. So we have to put these two equations in terms of binomial distribution, and then we will get a GIX. Okay, I think the question is the loss function will not be convex. Yeah, so basically for most of the cases, there are some distribution which shows that, like binomial distribution will again will make the loss function convex. Yeah, so there won't be any problem with binomial distribution or Poisson, definitely. But yeah, then there are so many distributions in the world, right? I cannot actually talk about those, but the most of the popular distributions are actually makes it very nicely differentiable kind of thing. Another thing that we can do, and we generally do, is that let's say when we see a quite a difficult kind of distribution, we first take a transformation, right? Let's say if we transform the data so that it falls into a kind of distribution which is with which we are familiar with. So that is also another thing that we do. this transformation is mostly linear or at least differentiable in some way, and when we try to do that. Another thing is that that is one thing. Another solution is that it has been seen that any data, and like if you take the scatter points, any data can be actually represented in a Gaussian mixture model kind of thing. So we are not covering Gaussian mixture model here, but the idea is that you do not consider one Gaussian over your data, but you consider a series of Gaussian with some weights. It's something like a weighted sum, where the summation is all these Gaussian distributions. So basically, you can consider the data to be Gaussian in parts. Everything can be represented in terms of Gaussian. It's just that they are a separate Gaussian. So that is called a mixture of Gaussians or Gaussian mixture model. And then you can model your data accordingly. So there is a separate kind of optimization that you do there. It's mostly a EM algorithm. It is differentiable. The loss function is differentiable, but it may not have a global minima kind of thing. Yeah, so in that case also we can actually handle the problem. It's not that we cannot handle the problem. You just have to take parts of the data. So means basically you have to model parts of the data separately using different Gaussians. So that is another way to do. I hope that answers the question. Okay, cool. Yeah. So we were talking about this particular case, right? We were about to finish. So basically, the simplification is here that all the covariance matrices of the data is same. So in that case, actually, we are dealing with D cross D parameters only, right? So in that case, it is a very nice thing. We get an equation. Of course, the constants here changes as per the calculation, and this also gives us a linear boundary. But that particular assumption that it should be orthogonal to the lines joining the mean is not there anymore, right? So it is little more flexible than the first case, and thus more generalizable actually. And the final thing is basically without any assumption. So we start, with the very basics of GIX, and we get this particular equation where these are basically the constants. And if we plot, we will see that this is basically a quadratic kind of decision boundary that we are getting, right? So quadratic comes because here you can see this is a polynomial equation for x of degree 2. That's why it will be always quadratics in nature. As we go with higher dimensions, it will be hyperquadratics. But then the number of parameters here to be estimated is the maximum. So if we are considering a d-dimensional space, so d cross d into n or k, let's say k is the number of classes. So k into d cross d plus k into d, where k d comes from the mean. So there will be d kind of parameters for mean, and for each class it will be kd. So quite a huge number of parameters that needs to be calculated for this particular Bayesian classifier. Yeah. So this actually leads to naive-Bayes classifier. Okay, we do want a very nice quadratic kind of curve, but we don't want to actually calculate so many parameters. So what other assumptions we can do? That is the question. So naive-Bayes actually assumes that the correlation between the feature points is 0. That means, when you consider the covariance matrix, it will be only diagonal. The diagonal numbers or that diagonal is basically the standard deviation along each dimensions or for each features. That will change, but the off diagonal terms are all 0. And then if we actually consider the thing that all the classes will have different covariance matrices, then also we get a very nice good quadratic kind of decision boundary, which is what we want. So in naive-Bayes, why is naive-Bayes so popular? One thing is that we get a fairly a quadratic classifier, so that is generalizable enough. If the data is such that it is linearly separable, it will be actually, it will be a linear boundary, of course. There is no harm in that. It can always simplify itself. But let's say for a complicated data, it will also give very good kind of accuracy or performance. It is only considering that there is no correlation between the features themselves. And then naive Bayes is mostly very much used in text classification. So I won't say that the features are quite independent to each other. For example, like uh, yeah, so we may mostly use some of the words in conjunction to each other, but still for like if we consider 1,000 words to be there in our English language, then perhaps only 20 or 30 will be very closely occurring with each other. Most of the other things will be independent of each other. So it does hold the assumption to a certain extent very well. So in that case, naive Bayes is actually a very good simplification of the original Bayes classifier. It does reduce the number of parameters, it does reduce the complexity of the classifier, and as the complexity of the classifier decreases, it becomes easier for us to train, it becomes easier for us to do the parameter estimation to find that particular bias variance trade-off, and nevertheless we get a very good decision boundary which can be as complex as possible or it can be simple enough. So that's why naive Bayes is very, very popular. But the whole intuition of naive Bayes and everything actually comes from the Bayesian classifier with certain assumptions, right? So yeah. Okay, so moving on. So this is all about about models and naive Bayes and everything. So as the question comes, it's basically definitely not the end, but we are just scratching the surface. This is like highly uh, means all these calculations are done keeping in mind that the distribution is Gaussian. That is a single Gaussian model only, but nevertheless it can get complex with different kind of distribution. It can get complex with different modalities of Gaussian. You can represent your Gaussian as a mixture model, and you can do the calculation. It can get as complicated as possible, or you can keep it very, very simple, as as discussed here. Yeah, so basically the possibilities are endless. Okay, so let's move on to the last part of this things. Okay, we actually have only 20 minutes, so I'll just rush away and try to go through the notebook as well. So basically there is this confidence intervals that I wanted to talk about. So let's say we have our data or the samples, and we deduce that there are some kind of the model is X% accurate on the test data. Now, how can we actually say that it actually represents the entire population? Or how can we say that at least I am 95% confident that this will have the true population will also have this 40% of accuracy. So generally this is where the confidence interval comes into picture. So there are many ways to calculate this confidence interval using different kind of distribution, Gaussian distribution, student tree distribution. So here in this slide, actually, I'm just giving one example using student tree distribution. So the confidence interval equation is something like this, where here S is the, S is the standard deviation, N is the sample size, T is something which needs to be calculated from the T table. And based on this particular data, that if my test set has 100 examples, accuracy so and so, and standard deviation so and so, then I am 95% confident that my accuracy of the true population will be in this particular range. That is what we want to say. So in many cases, like in many kind of evaluation of the model, you will see that in many papers you will see that there is this confidence interval mentioned with 95, 98% accuracy. So these are good things to consider, like 95 onwards, it's a good range of confidence intervals. So that is what it is being meant by this confidence interval calculation. So this does not, I'll say that, this we do not mainly use for training samples, training models or anything like that. But let's say when you But IEEE research papers, doing the evaluation of your model with the state-of-the-art models, these becomes quite important parameters, and this means this gives more strength to your paper if you want to represent your how much confidence interval you are talking about. Yeah. So another very important concept is the central limit theorem. So the question comes like, why do we always use Gaussian, right? So Gaussian distribution is very, very important. Most of the times I assume that, central limit theorem, or we assume that, underlying distribution is Gaussian. So this is mostly because, of the central limit theorem. So central limit theorem, what it says that, let's say you have a data which does not look at all with like a Gaussian kind of thing. But now you sample, you take some samples from the data and you take the mean of that and you try to plot the frequency of those means. So as you sample more and more, you will see that this mean, the curve of this means that you are plotting, it will get close to Gaussian. So how does it relate to? So let's say nowadays we always go for this, neural network, deep learning, where we do this batch process, batch wise computation, right? All this minimization using some batch and all those things. So anyway, we are anyway sampling certain points from our sample. We basically take a subset of the points, and when we actually consider the means of that, it is actually a Gaussian kind of thing. So basically, when you consider all these optimization techniques, most of the optimization techniques in your neural network training kind of thing, somehow down the line, the central limit theorem ensures that the whole algorithm that is there for this convergence and optimization using this batch size and everything, it follows nicely. The mathematical intuition behind it actually comes from this central limit theorem, right? That it is a Gaussian kind of thing, and you can use this calculations in a very nice way with the assumption that the underlying distribution is Gaussian. Yeah. Okay. So let's move on to the last concept, which is basically the hypothesis testing. So hypothesis testing is quite important in statistics. What happens is that given two hypotheses, we have to decide which one is more important to the other, important than the other given the experimental data, right? So there are these two hypotheses, null hypothesis, which is basically to be accepted or rejected, and then we put an alternative hypothesis as well. Again, which is basically an alternative to the null hypothesis. So we have to say like either the null hypothesis is correct or the null hypothesis is incorrect. Okay, so this is, if we are sticking to Gaussian, then we calculate the p-value or the z-score, and the less the so as the p-value decreases, it actually rejects the null hypothesis and the alternative hypothesis is considered favorable. So this table also shows like if the p-value is greater here, basically we are talking about a 95% confidence. So that's why this is 0.05 in that other way. So basically, if the p-value is increasing, then don't reject the null hypothesis. If the p-value is decreasing, then the alternative hypothesis is more stronger than the null hypothesis. Again, like how this is actually important. So hypothesis testing can be used for selecting models. And one of the most popular, or the early ways to do this is by using McNemar's test. So what happens is that there are these two hypotheses. Let's say we have two models, M1 and M2, and then we have to either see that like the two models perform in a similar fashion, or two models perform in a different way. So the null hypothesis is that two models perform in a similar way, and the alternative hypothesis is that the two models are actually different in terms of performance. So how do we do that? This is basically a contingency matrix, which are to be calculated in this way. You can see, both model one, these are the number of instances where model 1 and model 2 are correct. And these are the other things here, as you can see. And then the McNemar's test, as you can see, we find the chi-square, and then we calculate this particular equation here. And then if it is below our threshold, then we reject the null hypothesis. So that is the whole idea of McNemar's test. But then it can actually give a, statistically it shows a very significant result, or statistically it can say that whether two models that we are comparing are similar or not in terms of the performance with respect to the data that we have in our hand. Yeah, so that is how hypothesis testing are used mostly here, mostly in machine learning papers. Again, these are a little bit theoretical. Let's say you are reading any kind of paper, technical paper, research paper, then you will find these particular terms in terms of hypothesis testing, confidence intervals, and yeah, so these are basically the crux of it. Yeah, so I see that there are some questions. Any questions?
Dibakar was just discussing with me
Okay. Okay, cool.
the data issues here. So we are good.
Okay, okay. So let me again go back and try to share the, share my screen, and let me go through the hands-on sessions here. Okay. So yeah. So this is the actually the end of all the theories I wanted to cover, and there is basically a notebook which can be used for the hands-on session. So I thought I'll create all these things with you only, so that it becomes easier for us how to do that. So there is this GitHub link that has been shared to you all, and the comments are just, you just have to do this as per the instructions. Yeah. Okay, so git clone. Let me do a git clone. Yeah, this is just a terminal in my Mac. I'll
Suranjana, just let's ask everybody if they're able to uh, do these steps.
yeah. So could everyone do this? Means, yeah. Is there anyone who faced any issues?
Suranjana, I just probably would like to ask for the GitHub link, maybe in the chat window.
Okay, sure. In the chat. So this is the Git link. So all the notebooks and other things are here itself. Session wise, we have segregated it. So this should take a couple of minutes.
So all of you can just replicate what Suranjana is doing here.
So all these steps are here itself. You just it's always a good idea actually to create a separate environment for all the tasks, right? So it's just creating a Conda environment. So the environment name is tutorial. So this environment will have Python version 3.8. We activate the tutorial, we clone the Git repo here. You can either clone it directly using Git clone, or you can install, you can basically download the zip and copy it here. And then basically you need to install the packages. So these packages are actually, it contains all the things which will be covered in subsequent sessions as well. Yeah, so that's why it's taking some time, I'll say. But once you are done installing this requirements.txt, this should take care of all the other sessions as well. Yeah. So it's always a good idea to use environments for all these tasks, because what happens is that, for different projects, you may require certain versions. So most of the time, most of these packages, they do work very well with the latest version. But let's say this is a Python 3.8, but somehow down the line you need certain, for some projects you need to work in Python 3.6 or any other Python for the compatibility with others, with your team. So it's always good to go toward, create a separate environment and do all these things, create separate kind of packages as required. Yeah, so let's wait for a couple of minutes, means 1 or 2 minutes. It should be done.
So Harshita, were you able to clone it? Is Harshita on?
Yes, mom.
Okay, yeah. So the HTTPS was missing in your link, and that's the reason why you were getting that error.
Yes, mom, I'm trying again.
Okay.
to clone it.
Yeah, almost done. So if you want to clone any Git, so basically the idea is basically to go copy this here from here, do Git clone, and this particular, this particular link that is given by the Git itself, and you are good to go. Yeah. So it's done. So we'll open a Jupyter notebook. So the notebook that we want to use for this particular one is this tutorial 1. Okay, so these are basically all the concepts that we had discussed so far. I'll, in the interest of time, actually, I'll just go to each of those to show means what exactly I'm trying to do here. And but then these are pretty much, this has been explained in the presentation earlier, and it should not be a means it should be understandable now. Yeah, so we means for this package, for this tutorial, we only need 2 or 3, 4 I think 4 tools, which are very basic: NumPy, scikit-learn, matplotlib, and another statistical one. So first we generate this data. So basically what we are trying to do, this is a decision region we are trying to plot instead of decision boundary. So this is the range of the decision region. We are just, calculating the points which we want to consider in the decision region. This is the first case of the Bayesian. What we are trying to do here is basically, we have fixed mu and sigma, and then we are sampling points from this mu and from the Gaussian that follows this mu sigma. This is again sigma into I, where I is an identity matrix, right? So this is the case 1 of the Bayesian. We just quickly sample some points. Now this is our true, this is the data points that we had just sampled. Y true is basically the true labels, right? And this is how it should look. Yeah. So these are the magenta points, are all the points in our decision region that we will actually classify each of these points, and then we will, if we actually do it, color code it and plot, then we will see the decision regions very nicely. The black ones are the training points, or the point, not training points here, since we are already considering the parameters at first. So these are not our training points. So we need those mu sigma to be calculated from the training data itself, right? So now, since that we are already considering it, we do not need any kind of training the data. We will just do the testing on these points actually. Yeah, so the parameters for case 1, functions to calculate this, and the classification equation. So here we calculate, here we basically classify each points in the decision region, and also each points in these blobs, this black color points here. And now we will plot it using the color coded thing as per the class. So this is the case 1, right? So case 1, this is a linearly separable data. We get accuracy 100%. So this is class 1, decision region for class 1 in yellow, class 2 points, decision region of class 2 plotted in cyan. Accuracy for this red and blue points only, which we got as 100%, since it's a linearly separable data, right? So yeah, so this is a very nice kind of, it gives an intuition of what we just discussed about. So case 2, okay, so here priors for class 1 and class 2, I have always kept it as 0.5. So if you actually change it here, the line will, line will actually shift here and there. You can actually go later and change this, and you will see how the line decision region is actually changing, getting more close to class 1 or getting more close to class 2. So this is for case 2. So for case 2, what we are doing is basically we are assuming that the covariance matrix is same for both class 1 and class 2. This is again hard coded. You can anyway change that and see, how your decision region is changing, how the data is changing. You can all do that, right? So this is again a little bit different kind of data, because the covariance matrix changes, right? So the the sample points also changes, and this is the data that you have. So earlier the mean remains the same, but since the covariance matrix is different, the data that you see here is also changing. Now these are the constants, the classification parameters and the classification equation, and then we classify each and every points in the decision region, and each and every points in this data that we have, basically these black points here, points in the blob. And now when we actually plot it using the color codes, this is what we see. We get an accuracy of 97% for the black points. And as I said, this will be actually a linear boundary itself, but it does not mean that this linear boundary is orthogonal to the means joining these two classes, right? That is not happening here. Whereas in class first case here, this is a linear boundary which is orthogonal to the means, joining the orthogonal to the line joining the two means. So that is the difference between this particular case 1 and case 2. Now case 3 becomes more interesting, right? Now we are moving from we are moving from this linear to a non-linear quadratic kind of equation. So we should see significant change in the decision boundary. So again, like as the covariance matrix changes, the covariance matrix for class 1 and class 2 are different. So the data here also actually changes here, as you can see. The blobs change actually. Now we do the calculation. The number of parameters here you can see it's so huge. See, as we increase the complexity, the number of parameters also increase. We do the classification for each points in the blobs, for each decision points in the decision region, and see here we see a nice quadratic curve. That's what we see using the Bayes classifier. We get a very good accuracy, 99.5. So please remember that the previous data for case 1 and case 2, it was different. We were getting 100% accuracy for case 1, but please keep in mind that the data were different. Data means basically these blob points were different. It was linearly separable there. Here it is not that linearly separable because the covariance matrix has been designed in such way that there is little bit of overlap. So you can actually play with this covariance matrix here and the mean to make it more overlappy, more compact, more spread for the two classes, and you can see how these things changes. It's very interesting to visualize and see. So coming to naive Bayes, so for naive Bayes actually we have scikit-learn. Scikit-learn gives us very nice function, so we can actually calculate using this particular equation also. Here what we have to do is basically design the covariance matrix so that this becomes diagonal only. So if it is like 0.4 and 0.4 here becomes 0, then actually this will be a case of a naive Bayes. But for all practical purposes, we do have scikit-learn. We do use scikit-learn, quite a lot. You can also use this. Mathematically, you can also use this particular thing. Yeah. So for this particular data only, we are fitting naive Bayes. This takes some time. So I'm sure scikit-learn uses a lot of other functions for fitting. And now classification. Okay, so here what I have done is that for scikit-learn you need to pass some true for training data, right? So I've considered these blobs as training data here and this decision region as all the test points here. Okay, so you don't see any accuracy because this red and blue points becomes our training set itself, and it does not make sense to use accuracy on training set. Yeah. So no accuracy here, but you can see how the decision boundary is. So decision boundary is little bit less, less curvy in this naive Bayes. It is little bit more simplified than, case 3 of the Gaussian, where there is no assumptions, but nevertheless, it's a quadratic one. It is giving us good accuracy using this particular thing. So naive Bayes is actually a very good assumption or very good simplification of the case 3 of the Bayesian classifier. So little bit about bias variance trade-off. So what I did is basically taken a data set which is not at all linearly separable, used the Bayesian classifier 1, it gives a decision boundary of this. The concept is again the same, right? You deduce the mean. Basically, the mean and the sigma is being calculated from the data itself. There is no training here I have done in that way. So from the data itself, I have collected it and then calculated the class labels for each points in the decision region and all these points here, and plotted the decision region as done earlier. For case 2, Oh, did I run it? No. So, for case 3, this is case, oh, so okay, so for case 2 I ran. So case 2, it's again a linear boundary. Okay, so here basically the accuracy is 0.89, accuracy is 0.7, little bit difference in the accuracy. And then for this, this case 3, it's a quadratic kind of decision boundary where you can see you get 100% accuracy. Means it's the classes are well separable. It's just not that separable by a linear kind of decision line, right? So that's why we get 100% accuracy in case 3. So now basically the idea, if we compare, case 2 and case 3, this is a kind of correctly fitted model, whereas this is a underfitted model with high bias and low variance, right? So that is what we were discussing here. This one also low variance, high bias. Whereas I won't call this, this is actually very much applicable for this particular data. So like even if some points come here and there, it's not very tightly fitting also to this particular class, the points from this data. Shushmita, you want some annotation request? Or you pressed by mistake? Okay, I'm going to finish that. And in case you don't require, please, remove the request for annotating. Okay, so another thing is basically the statistical significance or the hypothesis testing, right? So this is one package, this is one that McNemer's test that I was talking about. So what it does is basically, let's say whether this, for this moon and blob data, whether case 1 and case 2 are, significantly different from each other. So what we try to do is basically, we try to calculate this contingency matrix, basically, the amount of points, what is required is basically the amount of points which are labeled true by one model but false by the other model, and vice versa. So basically for this particular thing, like for this particular package, you need to find all the contingency metrics, but the most important term is this C10 and C01. So if we just consider, if the models of case 1 and case 2 are different or significantly different or same, we consider these two particular thing, and if we run it using the results that we have said, statistically these two models are same. So even if you say that there is 2% increase or decrease, statistically it is not relevant. However, let's see if we try to do with model case 3 and case 2. So it clearly says that statistically one is better than the other. So if you want to put some statistical significance to the comparison of the models that you are comparing, you can use this hypothesis testing. Yeah, so you can play with this. Also with different mu, sigma, you can actually go ahead and see how things change with different kinds of toy data. Even like this is a non-linearly separable, what happens, if they are non-separable, how things are changing with different priors. So all these things you can change here and see how, how the algorithm works. Yeah, so this is what it is about. It mostly covers all the concepts that we were just discussing now.